You would all be able to tell me that molecules are made of nonmetals. The bonding in molecules is covalent. What does it mean to be covalent? The electrons are shared, yes. Describe a formula unit. It's a single unit of the ionic crystal. Yep. Overall, it is neutral, but it is made of anion plus cation. If you have a cation and an anion, which one is the metal and which one is the nonmetal? Cation is the metal and anion is the nonmetal. Excellent. All right, that was just a quick little review of some of the stuff from last day. If you're knowing that, you're probably all right. Okay, let's see what else we've got. Oh, I have notes on making a solution from the lab. Is there anyone who wanted a copy of those notes? Come on up and grab one if you would like a copy of the notes from making a solution from the lab. The lab is on your test, okay?
You're so cool, Miss Spence. Thank you.
And if we run out, let me know. I can make more.
And Miss Spence, I forgot to do my lab too.
We'll sort it out. We'll get you caught up. It's all right.
All right, thank you.
Okay.
Take one. Thanks.
Yeah, math. Good.
I just need I completely forgot to hand in the lab. Can I work on it?
Oh, yeah, absolutely. Yeah, no worries.
I have to do it next week.
Yeah.
So I won't be here till-
Yeah.
No, I meant more of, I don't know if you know what about.
We need them. Who else needs a copy of the notes? Did not get them. I'll make another 5 or so, okay? All right, no worries.
Should be in here. Yes.
Okay, we're going to take a quick look at page 126. So this is about solutions, okay? Page 126, 126. Yeah, it's at the very end.
What happens when stuff dissolves?
Okay, let's make it bigger. There we go.
I mean, like, what happens to the atoms and molecules that make it up? I want to talk about 2 things here that you dissolve all the time: salt and sugar.
You should already know what happens with salt. Tell your neighbor what will happen to those blue and red things, the cations and the anions, when the salt dissolves. Tell your neighbor. Okay, let's take a look and see if you were correct.
These two things look very similar. They're both like kind of white powders made up of little grains, and you can pour both of them into water and stir around, and you see the grains get smaller and smaller and maybe break apart until eventually they've totally disappeared. They've completely dissolved in the water. That's what you see with the naked eye. But if you had atomic vision and you could see the atoms that make up salt and sugar, what would it look like as these grains broke apart and became invisible? That's what we're going to talk about here. So it actually depends whether something is an ionic or a covalent compound. It depends on what it would look like when it dissolves. So over here we have salt, and this is an ionic compound. This is what a grain of salt would look like, and it's made of sodium ions, Na+, which are metals, and Cl, chloride ions, these blue things here, which are nonmetals. So salt is an ionic compound made of metals and nonmetals. Sugar, on the other hand, is a covalent compound because it's made of nonmetals, carbon, oxygen, and hydrogen. And these nonmetal atoms are connected together into a molecule. So a grain of sugar would look like this. It would be a bunch of these sugar molecules all kind of lumped together. Notice that a grain of sugar is a lot more messy. It's not nearly as well organized as an ionic compound, this grain of salt over here. Anyway, let's look at what would happen when we dissolve these. We'll take a grain of salt, dip it in the water, and start stirring around. With our atomic vision, we're going to see that the atoms that make up this salt are going to come apart from each other. They're going to break apart, and they're all going to start floating around in the water individually. This is what it looks like when salt dissolves. Okay? Now let's take our sugar. Here's our grain of sugar. It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water.
Okay, so let's think this through. We got sugar molecules, yes? And as a solid, if we go back, where are they? Okay, so here's our little solid here. And this is made of many sugar molecules stuck together. What is holding those sugar molecules together? Intermolecular forces. Are intermolecular forces strong or are they weak? They are weak. So water can replace, like sugar has a positive end and a negative end. Water has a positive end and a negative end. The water can kind of take the place of another sugar molecule and be like, hey, bond with me instead. Yeah? What kind of bonds are between the atoms in this sugar molecule? Those are covalent bonds, shared electrons. Are those strong or are they weak? Those are strong. So water does not have the ability to break those bonds. Water can break the weak intermolecular forces, but it cannot break the strong covalent bonds. Okay?
It goes in the water, we stir it around, and the grain of sugar is going to break up like we saw the grain of salt break up, but it's going to break up in a different way. It's going to break up into the individual molecules that made it up. But these molecules are not going to break up into the individual atoms. They're going to stay as molecules, and those molecules are going to start floating around in the water. A big mistake that people make, I don't want you to make this mistake, is they think that when sugar or other covalent compounds dissolve, they think that the atoms that make up the molecules totally break apart. And then you end up with a glass of water that has all these carbon and oxygen and hydrogen atoms just floating around. That does not happen. Big red X. Instead, the molecules stay together. Well, the atoms in the molecules stay together. So this is a big difference between how covalent compounds dissolve, where the molecules stay molecules, and how ionic compounds dissolve, where the grains of these things like salt actually break apart into the individual atoms.
Okay, so that's basically all there is for that. We're gonna go make sure, yes.
So with sugar, like specifically, if the water is room temperature and you put sugar in there, it's
Yep.
going to dissolve.
Yep,
Once it starts to heat up and it starts to melt the sugar in the water, what happens then?
you don't need it to be heated up for the sugar to dissolve. Sugar will dissolve in room temperature water.
But over time, like,
Yeah, I mean, if you stir it, it'll go faster. If you heat it, it will go faster. The reason is that it dissolves by what, actually, why don't we take a look? Okay, there's another Tyler video that goes into a little bit more depth. All right, and that is this one.
3D models of water molecules.
So here we are.
In this video, we're going to talk about how things dissolve in water to make aqueous solutions. We're going to look at an atomic view of how water molecules dissolve solute particles, which is a process known as solvation. And we'll see that solvation occurs differently for covalent and ionic solutes. Let's start by making an aqueous solution, one that you've probably made yourself many times. We'll dissolve a sugar cube in water. So here, sugar is a solute and the water is the solvent. We're making an aqueous solution of sugar. Now, if you've ever dissolved a sugar cube in water, you know it takes some time to dissolve. It's not instantaneous. Let's take a closer look at what's happening during this dissolving process. Here's our sugar cube, and let's imagine that we could zoom into it many times and see the atoms and molecules. We'd see that the sugar cube is made of trillions and trillions of molecules that look like this.
Okay, so you can see we have carbons and oxygens. Actually, it's really hard to see. Oh, we've got a blown up one on the bottom of page 127. You can see there's carbons and hydrogens and oxygens all over the place, attached in little rings and sticking off the ends and things like that. Okay, C12H22O11. All nonmetals, so they are all bonded covalently. Covalent bonds are strong.
Table sugar is actually a compound called sucrose. Here's its chemical formula. And it's made of carbon, hydrogen, and oxygen atoms. Because these elements are all nonmetals, you know that sugar is covalent. Its atoms are connected by covalent bonds made by sharing electrons. And there are different ways that we could show the molecule. So here, we're representing the sugar molecules with a 2D Lewis structure that shows the covalent bonds. If you made this into a ball and stick model, it would look like this. But a more accurate depiction of sugar is actually closer to this. We call it the 3D model.
Also known as the space filling model. So you've come across those before, yes? Okay. So we have our Lewis structure. This year you will be learning to draw Lewis structures, but not for anything nearly as complicated as sucrose. Did you learn Lewis structures last year in grade 10? Anyone? Some of you. Okay. So if you didn't, it's okay. I will take you from scratch all the way up to being a Lewis expert. All right. Ball and stick. The atoms are the balls. The sticks are the covalent bonds. And the 3D model just shows the overlap of those atomic orbitals that allows them to share electrons. Okay.
It's a bit blobby and kind of hard to see all the different atoms. But we're going to use this model for now because it will better illustrate what we're talking about here, which is how molecules interact. Now, let's look at water, which is our solvent. Water has a chemical formula of H2O, and here's some 3D models of water molecules. Now, we want to look at dissolving here. So let's zoom in on our sugar cube in the water. We're going to look at this edge right here.
We're now on 128.
So here's the edge, zoomed in millions and millions of times. The sugar molecules are all clumped together. This looks pretty confusing, so we're going to clean it up a little. We'll reduce the number of sugar molecules and we'll arrange them in neat little columns. See? This is easier to look at. But just remember, things are more messy in real life.
Okay, and we're just going to take a moment and we're going to draw in some intermolecular forces. All right, on our little picture. Okay, so we have 128. There we go. Okay, so here in between we're going to have forces there, some forces here, and that is an intermolecular force. How do we abbreviate that? IMF. Okay, and then we have some intermolecular forces here as well. And I'm trying to get it to go between the red and the white, although I know it doesn't look nearly as beautiful in your book because red attracts to white because the red is negative and the white is positive. Oh, yeah, that's right. And then the white is positive. So I got some red here, and that's going to attract to that white there. And we've got a red and a white and a red and a white. There's also repulsive forces. Okay, the positives will repel positives, but overall you'll end up with a net attraction. Okay, I'm not going to draw in anymore because it gets tiring, but that's what we're looking at there. And remember, the intermolecular forces are weak.
Also, remember that this sugar cube is sitting in water. So now let's add the water molecules that are on the edge of the cube over here. There we go. We got the water and the edge of the sugar cube. Now, for the water to dissolve the sugar, water molecules have to bump into the sugar molecules. They got to bang into them, sort of like this. And they can only do this at the surface of the sugar, so it takes some time.
Okay, so that's why it takes time, because the water can't bang into sugar molecules that are in the middle of the crystal, right? Because they're tucked away inside. And if they bash in with more speed, will that knock the sugar molecules loose more easily?
No.
Yes. So if you stir it, the particles move faster, which means the water molecules are bashing into the sugar faster, which means with more energy, and that they're more easily knocked loose. Same thing, if you heat it, the particles move faster, which will mean that they can knock them loose more easily because they're bashing into it with more energy. Okay? And while we're at it, we're also going to draw in some intermolecular forces in between the waters, the positives and the negatives. So you could even draw in like a negative and a positive here. These ones are easier to draw. Sugar molecules are complicated. Water is nice and easy, okay? And we have, let's see, these aren't really arranged very nicely. I'm noticing a lot of, oh, here we go. There we've got a positive and a negative. And we have a positive and a negative. We got a negative and a positive. All right. Again, these would be all over the place, but I don't want to draw them all in. You basically end up with like a big, huge spider web almost of these IMFs. But guess what? If we zoom in here, we've got some positives on this water molecule. And what do I see right there? That right there is negative. I've got a little red negative. Okay? And I've got a red negative, and it's going to bump into this little positive. So we're going to be breaking intermolecular forces between the sugar molecules and forming intermolecular forces between the water and the sugar. BW is between. Sugar, do you guys remember the abbreviation for molecule? MC, molecules. And the second thing we do is we form IMFs between sugar and water molecules. So here are our little IMFs, white to red, white to red, red to white, white to red, red to white. Yeah? Yeah.
Also, like, now we put steel in water, it forms rust, or it forms.
Oh, that's a chemical reaction, not a physical change. This is a physical change because the sugar is still sugar.
Yeah.
Okay?
But then rust becomes a different.
Rust is a different substance. So you actually have a reaction between the iron and the oxygen in the air, and the water helps it take place. Okay? Okay.
Then, after bumping into the sugar, the water molecules kind of work their way in between the sugar molecules and surround them. You can see that happening here. Once a sugar molecule is surrounded by water molecules, they carry it into solution. Here, you can see that one of the molecules of sugar is surrounded by water molecules and it's carried away. Now, keep your eye on this one here at the top. And there we go. It got surrounded and carried away.
Okay, so we can fill in those boxes at the top of page 129. The water molecules do what?
Kidnap each other.
They collide into the solute. And then what does the water do? It surrounds the solute. And then what does it do? It kidnaps it. It carries it away. So they bash into it, they surround it, and they carry it away.
Oh, wait, can I?
Yeah, I'm going to just keep it paused here for a moment. So these are going to be the boxes at the top of page 129. Water molecules collide into the solute. The water surrounds the solute. And the water carries the solute into solution. Okay.
As the water molecules carry the sugar molecules into solution, new water molecules can reach the undissolved sugar over here, and the process continues. I think this one's next, and there we go. Another one gets surrounded and starts to float away. And this is what's happening at the atomic level as sugar dissolves. All these sugar molecules are coming apart from each other, and they're getting surrounded by water molecules, and they're floating off into the solution. Now notice one thing here about how the sugar molecules float away. This is super important. The sugar molecules separate from each other, okay? But the whole molecule stays together. The molecules don't break apart into their atoms. In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule. The atoms in the molecule stay together as the sugar dissolves. So, as you can see, we have 3 molecules that have come off the surface so
Okay,
far,
so
and they break the
did
covalent
we catch everything
bonds.
here? Or do we need a pause? Let's get his arm out of the way.
The whole molecule stays together. The molecules don't break apart into their atoms. In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule. The atoms in the molecule stay together as the sugar dissolves.
I missed it again. And there was his hand. There we go. Okay. And then at the page, at the bottom of the page, we're just going to bop over there for a second because I want to correct something. Oh, it's thinking hard. It doesn't like it when I'm doing too many things at once. This is not a very powerful processor. Okay. Okay, it says this will not be on the test. Let's cross that out and let's put this here is not on the test because you should know what type of force or bond is breaking between the sugar molecules. Intermolecular forces. So basically we're saying dissolving does not break the covalent bonds because they are strong, but it does break the IMFs because they are weak. And if you're going to take biology, the specific type of IMF is called a hydrogen bond. That is interesting, but you don't need to know it for this level of chemistry, okay? But you would be using that in biology. All right.
So they're always hydrogen bonds no matter what?
Hydrogen bonding is quite a complex thing, which I'm not going to go into right now. It's a type of, we call them dipole-dipole attractions or dipole-dipole forces, where you have a polar molecule that has a positive end and a negative end. It's called polar because it has a positive pole and a negative pole. And another polar molecule that has a positive and a negative end. All right. Hydrogen bonding is a specific type of that. It requires specific things, like it needs a hydrogen to be present, and that hydrogen has to be bonded to either oxygen, nitrogen, or fluorine.
Oh,
Okay. But like I said, that's more than we need to know for this point in the course. And what have I done with that little pen? I have no idea. That's okay. I have this one. So life is all right. Okay. And we're just going to keep going with the video now. Okay. Go.
In other words, the dissolving process doesn't break the covalent bonds inside a sugar molecule. The atoms in the molecule stay together as the sugar dissolves. So, as you can see, we have 3 molecules that have come off the surface so far, and this process will keep happening, pulling more and more sugar molecules into the solution. Let's zoom back out and look at our glass. And here we are. We were just looking at one side of the cube, but this dissolving process is happening all over, on all the different sides, anywhere that's touching water. Now, after the dissolving is complete, all the sugar molecules will have been pulled away from the cube, and the cube is gone. And if we could zoom in and look at the liquid here, we'd see that the sugar molecules are mixed in with the water molecules, spread all throughout. So this is what a solution of sugar dissolved in water would look like at the atomic level. Now, as we've seen, a big part of dissolving.
Okay, now we're going to just pause for a second because we have one more thing on here. If I can get this to move for me. There we go. So this process where we have C12, H22, O11, solid, it dissolves and it forms C12, H22, O11, and then what is the state? Aqueous. Do you remember how the ions actually split apart? We had NaCl together, and then we had Na and Cl separate, or the calcium and hydroxide together, and then we had calcium separate from the hydroxide. Covalent compounds do not do that. Covalent compounds stay intact. Okay? Each molecule stays intact. Okay? The molecule stays intact. In an ionic compound, the formula unit comes apart into separate ions. The crystal lattice comes apart into individual ions. Okay, so there it will look like just a little ball and a little ball and a little ball, whereas these are like, there is our intact molecule. Okay, and this process is called dispersion. Do you know what it means to disperse? The crowd dispersed, separated. So dispersion just means that the molecules are separating from the other molecules. Is good? Okay. So you'll notice that the formula is the same. Yes? The molecule stays intact. So are we feeling pretty good about our covalent compounds? All right. So we are now going to go on to, well, I guess we're going to talk about solvation first. Solvation! I always feel like I'm going to be like some southern, preacher, because they're always like, salvation! And I'm like, solvation! Sounds exciting, but I don't know if it's that exciting. All right. Let's carry on. Here we go. It's a weird little world we live in here.
Gets surrounded by molecules of solvent. There's a special name for this process. We call it solvation.
So you can fill in that first box, solvation. I know he's got his hand over it, but the word is right above it as well. And when it is when a solute particle is surrounded by molecules of the solvent.
And we use the term solvated to refer to solute that is surrounded by solvent molecules.
Okay, so we have solvation, which is when a solute particle is surrounded by molecules of solvent, and this particle has been solvated. It is surrounded by solvent particles. And specifically, if that solvent is water, instead of just saying solvated, we can say it is hydrated. So it is when a solute is surrounded by water, which is the solvent, and of course, hydro is water. Okay?
Now, if the solvent is water, like it is here, you can be extra precise and you can say that these molecules are hydrated. When we say a solute particle is hydrated, it means the same thing as solvated, but we know the solvent is water. These little clusters of water molecules surrounding a solute particle are called hydration shells. You might also hear them referred to as solvent cages.
Okay, so they might also be referred to as solvent cages. So we have our hydration shell. This is our solvated or our hydrated particle in the middle.
They make this little cage or shell around the solute. Just keep in mind that they surround the entire solvated particle. So they're actually in 3D, right? Even though we're just drawing them in 2D here. So that's hydration shells or solvent cages. Now, let's switch gears here and see how ionic compounds dissolve. Sugar, which we looked at earlier, that's a covalent compound. But the process of solvation works differently for ionic compounds like sodium chloride or table salt.
So what kind of elements are these made of? Metal and non-metal. What kind of bond holds them together? Ionic bonds. Shocking, because it's made of ions, ionic bonds.
We know that sodium...
Oh, and in an ionic bond, what happens with the electrons? Are they shared? No, one atom gives the electrons, the other one takes them.
chloride is an ionic compound because it's made of a metal, sodium, and a non-metal, chloride. Here's a grain of salt. If you could zoom down to the atomic level, you'd see that a salt crystal is made of trillions of tiny ions all packed together. Sodium ions have a positive charge and chloride ions have a negative charge.
And actually, I didn't put like a little thing on there, so you could add in somewhere, maybe just above the sodium and the chloride, that they are bonded by electrostatic attraction. That's really big words for positive and negative attract each other. Okay? What is electrostatic attraction? It has to do with electric charges, hence the electrostatic. And so they are bonded by electrostatic attraction. Write that in for yourself. They are attracted just like magnets are attracted because positive and negative attract.
These ions are bonded together by electrostatic attraction. It's kind of like trillions of tiny magnets all stuck together. So, let's see how solvation happens with an ionic compound. We'll zoom in to get an even closer look. When you put sodium chloride in water, the water starts bumping into the ions at the surface of the crystal.
So we are now on page 132. Oh, we do have it. Oh, look, on the next page, it says like, on 132, bonded by, you can practice writing electrostatic attraction again. It's a weird, big, long word. You might as well write it again on page 132. So they are bonded by electrostatic attraction, like magnets, but not magnets. And then what do the water molecules do? They bump into the crystal. All right. Let's carry on.
And then the water molecules surround the ions and pull them apart and carry them into the solution.
So on the bottom of the page, you can, let's just go back a little bit. He's on to the next thing now. There we go. There we go. Water molecules bump into the crystal. Water surrounds the ions, and the ions are pulled apart into solution. That's the diagram at the bottom of page 132. Okay.
The water molecules surround the ions and pull them apart and carry them into the solution. Now check this out. What we're seeing here is that for an ionic compound, the individual ions get pulled apart during dissolving. This is different from what we saw with sugar. This process, we call it dissociation. Dissociation is how ionic compounds separate into ions in solution when they dissolve.
Okay, so you can fill that in. Individual ions get pulled apart, and dissociation, ionic bonds separate into ions in solution. Now, do you remember what it was called when the sugar molecules separated from one another? That was called dispersion. Ionic compounds don't disperse, they actually dissociate. Do you know what it means to associate? If you associate with someone, you meet with them, you come together. If you dissociate, you break apart. So the ions break apart into their ions.
So, when salt is dissolved in water, it dissociates, it comes apart into ions. Let's zoom out here. Remember that dissolving happens all over the surface of the salt. Once a dissolving is complete, the ions are spread throughout the water. So let's stop to compare how water dissolves the two different compounds that we saw.
Okay, so we're running out of time. The bell is going to go. Oh, no, we have 5 more minutes. Okay, we're good. We'll be able to finish this. It's all good. Okay. So we are now on page 134. The covalent solutes stay molecules. The ionic solutes dissociate into ions. The molecule remains intact. The ionic solute dissociates.
Sugar is a covalent compound. It's made of molecules. When sugar dissolves, the molecules move away from each other into the solution, but they remain intact. The water doesn't break the bond between the atoms in each molecule. But on the other hand, salt is an ionic compound. It's made of ions. When it dissolves, it dissociates, it splits apart into positive and negative ions. Now, let's look at dissociation here a little more closely. One thing you might have noticed about the diagram is that the water molecules are surrounding the ions a bit differently.
What do you notice about the water molecules around the sodium? Yeah, the red part, the negative, faces the positive ion. What about around the chloride? The white part, which is the positive part, faces the negative ion.
For sodium, their oxygen atoms face the ion. But for chloride over here, the hydrogen atoms are facing the ion. Why does water form these two different types of hydration shells? Well, we have to mention something about water here. You may know that water is a polar molecule. That means that a water molecule has partial charges, very weak electrical charges at different ends of the molecule.
And if you're like, what is that weird little symbol there? That is the Greek letter delta. It's not a capital delta. You're probably familiar with capital delta from math, maybe. Okay, that's a capital delta. This is a lowercase delta, which is like a Greek D. Okay, delta. And delta means slightly or partially. Okay, so if you want to draw it, you start here, you go around in a circle, and then you kind of go like that. It should not look like an S. It should not look like a D. It should look like a delta. Okay, not an S, not a D, a delta. So practice drawing that a couple of times. Okay.
The two hydrogens here are partially positive, and the oxygen is partially negative. These polar charges are much weaker than full charges on ions, but they're still important. This polarity has an effect on solvation. The partial charges are attracted to the ions. When water molecules approach a positive ion, like sodium here, the partially negative oxygen is attracted to the positive ion because opposite charges attract. And the partially positive hydrogens are repelled because like charges repel. The exact opposite happens when water molecules approach a negatively charged ion like chloride. Here, the partially positive hydrogens surround the negative ion like this, and the oxygens are repelled by the negative ion because they have a partial negative charge. This pattern also shows why water is so good at dissolving ionic compounds. The partial charges are attracted to the ions, the water surrounds them, and then carries the ions into solution.
Okay, we will finish that up next time, but your homework is pages 122 to 125, which covers a lot of these same topics. If there's any questions in there that we haven't covered in today's lesson, we'll deal with them tomorrow. Okay, so if you come across something that we've not dealt with, you can ask about it tomorrow. 122 to 125. Enjoy your shortened day and your afternoon. It should be beautiful for you. It's sunny out there. Hi, you have a quiz to get back, don't you? Yes. Now I have it. It is in my bag, which is here. If I'm lucky, that's it. No, not that one. It's the one. There you go.
Did
Hi.
you mark yesterday?
Not yet. No. Okay, it'll be done for tomorrow. Yeah.
Did I miss anything, or should I be good
Let's
by
see, what
just
did
looking
we
at the
do
teams?
yesterday? That's a good question. Let's just press stop here.